All right, so anyway, I think we should start. So for the last talk of the day, it's my pleasure to welcome Judith Rousseau from Université Paris-Dauphine and NSAE. Judith is an expert in Bayesian statistics and nonparametric Bayesian statistics. And she's working on proving frequentist results for Bayesian methods. So how about unifying the two methods? So I've heard once that not all Bayesian methods are good, but all good methods are Bayesian. And she's actually proving this kind of things for which Bayesian methods are good.
Okay, thank you. Thank you for the invitation. So it's great that I'm talking after Mike because I'm the same. I'm doing half Bayesian, half frequentist. And my point is, so his story is that he was in MIT and there was no statistics, and I was in France and there was no Bayesians. And so I became a bit of a mixture of things. So the talk, I'm going to sort of describe the general setup, which is like Bayesian statistics, in case you don't know, Bayesian nonparametrics, the kind of issues that I'm interested in, and also how we can answer these issues looking at asymptotics, and in particular the frequentist asymptotics. I was in Paris this morning, so I'm a bit tired. And so if you don't understand me, just shout. It means that I've gone off my mind somehow. Then I'll get into things that I think are quite interesting and are open question mostly, which is measures of uncertainty related to Bayesian procedure and frequentist procedure, actually. And so there are many ways of looking at these measures of uncertainty. One is looking at concentration rates because it gives you measures of risk. The second is looking at confidence regions. It's another way of thinking about it. And now I'll be sort of looking at it in two types of ways. One is purely nonparametric. The other one is semi-parametric. And then I'll discuss what I think are important questions and various directions that people are taking nowadays in these kind of areas. So Bayesians, you have a sampling model, which is with data x, xn, because it's going to be asymptotic. Theta is a parameter, so theta can be anything. It can be infinite dimensional. It can be a set of topics or whatever. And you have a distribution on these that's indexed by theta, p theta. And you're Bayesian. You're going to be Bayesian for the next 20 minutes. And so you have a prior pi on theta. The Bayesian approach, as you all know, is looking at the posterior distribution. So you're looking at the distribution of theta given the observation. And we are looking at models that are dominated. In other words, the posterior distribution is proportional to the likelihood in black times the prior in red. And you have the marginal at the denominator. But we are going to be essentially interested not so much in the marginal. Just to illustrate the kind of things that you have in very baby models. So if you were looking at a very simple model, what you would have, let's say, assume that you have Poisson random variables with the parameter theta and a prior, which is a gamma. Then for a small n, you have, so in red you have the prior, and in black you have the posterior. And what you see is that actually the picture varies not so much when some of the hyperparameters in your prior are changing. So you have two different sets of hyperparameters in the left and in the right, and you have two different sample sizes in the upper row and the bottom row. And the question is now is that how can we extend these observations to more general models, and in particular to large models? And the talk is going to sort of answer this. What you see in the pictures is that you have a concentration. The posterior distribution is concentrating towards the truth. And how can you extend that to infinite dimensional models, typically? The other thing that you're observing is that there is a Gaussian shape of the posterior distribution. How true that is when you have infinite dimensional models or complex models. And the last thing that you have is that how influential is the prior? What do you forget with as n increases, and what don't you forget? And that's sort of the questions that I'm going to try to shed light on, at least. And so So the first question is, so if I go back to what Mike was saying in his talk, if you have a loss function, so the decision theoretic approach, you have a loss function. The frequentist procedure is to have an estimator and to look at the risk. From a Bayesian perspective, you have a Bayesian estimator, which has been described by Mike. And somehow, if you are interested in the frequentist properties of this Bayesian estimator, or the frequentist risk of this Bayesian estimator, what can you say? And if you look at the posterior concentration rates, which we are going to do afterwards, you're going to answer the first question. Another question of interest is looking at credible regions. So there are measures of regions of uncertainty. In other words, it's the region for which most of the mass is. And you're going to look at the smallest region, more or less, such that most of the posterior mass is in this region. So the posterior probability that theta belongs to the region is greater than 1 minus alpha. This is a credible region. And the question is this credible region also a confidence region asymptotically, or to which extent can we say something like that? And that's a difficult question. And for the moment, we only have partial answers, and often we don't have like positive answers. And we could talk about testing, but here I'm not going to talk about that. So as I said, looking at posterior frequentist risk, you can if you are frequentist, you could also look at a Bayesian estimator and think that's an algorithm. Is it a good algorithm from a frequentist perspective? So you look at the frequentist risk, and that can be answered using the first kind of tools I'm going to describe. The second is, what can you say about the measures of uncertainty? And that's a difficult question. So Bayesian nonparametrics, as Mike was describing, a complex model, which was nonparametrics. You have all sorts of nonparametric model, of course. For instance, you could look at regression model. So you want to estimate a curve, which is in L2. You could you have density estimation or conditional density estimation. So you want to the object of interest are densities or families of densities. You can do classification. You can do spectral density estimation. So you can do all sorts of things. And in each case, your object is infinite dimensional object or families of curves and things like that. So you put a prior on these guys. So what are the typical kind of priors that you can come up with? The most common one is the Gaussian process. And that's very useful if you are working in L2. So if you are on something that's a curve that's not necessarily positive or things like that. So a Gaussian process, I think a lot of you know what they are. They are very nice objects. They are driven essentially by their kernels, so the covariance kernel. And depending on the structure of the covariance kernels, you have a very different prior. For instance, on the left, I have a Brownian motion, so you have a very irregular prior. And on the right, I have an exponential kernel, so you have a very smooth prior density. And interestingly, when you have such objects, the smoother you are, the tighter the process is around the curve. So you have not only a very smooth curve, but you have very narrow bounds as well. And that's very important because you're not only interested in a point estimator, but you also want measures of uncertainty. And that's all what a statistic is about, isn't it? While you have all sorts of ways of sort of going around these ideas, instead of looking at Gaussian processes, you can expand your function in bases. It's sort of the same ideas. And then you can use hierarchical constructions. There are all sorts of ways of doing that. Another families of models, which is sort of close to what Mike was describing, are mixture models. Again, you can decline them. You can sort of make them vary according to the context. But the typical example is when you do this density estimation, and then you look at a mixture of Gaussians, for instance. And then you put a prior on the mixing density P, distribution P, sorry. And the most common prior on P is the Dirichlet process that Mike was talking about. And you end up with an infinite mixture, but with discrete components. So the question is, in each of these cases, you have hyperparameters in each of your models. For instance, if you take these exponential kernels, you have the A, which is for the Gaussian process. If you take these random series, you have the variances of the theta i's. If you take a Dirichlet process, you have either K or you have the prior on the weights and things like that. So each time you have hyperparameters that come in the prior, and the question is how influential they are. And is their influence going to decrease as n goes to infinity? As the number of, when the information increases, can we forget the influence of these hyperparameters, and which one disappear, which one don't disappear actually? And the one that don't disappear asymptotically, you really have to be careful about them. So there is a large now literature on Bayesian nonparametrics, or frequencies Bayesian nonparametrics. The first results were due to Lawrence Schwartz and Baron and Vossum, and then afterwards were on consistency. So it's sort of the weakest requirement that you can ask, and you want a procedure to, when you have a lot of observation, you want to be a posterior to be close to the truth, to concentrate on the truth. But so then people started thinking, okay, it's nice to have that, but at which rate is it going to concentrate on the truth? So you're looking at balls around the truth, and they shrink towards the truth, and at which rate can we make them shrink, but still containing most of the mass? And that's posterior concentration rates, and it sort of started to be of interest for people from the 2000s with a seminal paper by Ghosh, Ghosal, and van der Waart, who gave the main tools to look at these kind of things, and I'm going to describe these tools afterwards. And then more recently, like much more recently, actually, people started thinking about what about measures of uncertainty? What can we say about them? And that's, to be able to say something like that, you have to have a very precise description of the behavior of the posterior distribution. And that's typically done through looking at what we call Bernstein-von Mises theorems, or things like that, and that's only there are only now a few results on that. It's a growing literature, but it's going slowly. And I'm going to describe these kind of things. So consistency, how do we define that? Well, you said the posterior is consistent at the truth if it concentrates around the truth. So for each epsilon, so you're looking at each neighborhood of the truth, and you want asymptotically, as the number of observation increases, that the posterior distribution of the posterior probability of these neighborhoods goes to 1. Whatever the neighborhood you're looking at, the posterior probability of this neighborhood must go to 1. Now, concentration rates, same idea, except that instead of looking at fixed neighborhoods, you make the neighborhood shrinks. And we were interested at the fastest rate as possible, such that the posterior probabilities of these shrinking neighborhoods still goes to 1. And the rate at which these neighborhoods shrink is called the posterior concentration rate. And I will talk about minimax posterior concentration rates when I'm looking at truth, so theta naught, the true parameter belongs to a class. And actually, the epsilon n that I get over this class is exactly the minimax rate that is obtained in the frequencies literature. So when I talk about minimax concentration rate, it's only because we have the same results as the frequentist, essentially. So what are the main tools that Ghosal, Ghosh, and van der Waart sort of provided to look at these posterior concentration rates? And actually, they had a very nice theory that says that you only have to look at 3 conditions to get these rates. And the first condition is what we call the Kullback-Leibler support condition. And in other words, what you're asking is that the prior puts enough mass on Kullback-Leibler neighborhoods of the truth. So you look at small neighborhoods, and it's a bit like a bias and a variance condition for the prior, in other words, because the epsilon n which describes the size of the Kullback-Leibler neighborhood, is the same as the epsilon n that gets on the. Do I have a pointer or something? Yeah. It's the same as this epsilon n here. So here you have the bias, and here you have the variance. Somehow you can look at it like that. So this is the first condition, and this condition is here to bound from below this denominator. And then what you're asking is that the prior puts mass around the truth, and the prior is not too complex. In other words, you can find a sequence of sieves that converge to the whole parameter set, which contains most of the prior mass, and such that on this sieve you can test uniformly whether theta is equal to theta naught against theta is away from theta naught at a distance epsilon n. And so in other words, the neighborhoods that you're looking at are driven by the geometry, which is driven by the loss function d. And this loss function d only enters into these sets. Otherwise, it's driven by the Kullback-Leibler divergence, because it's based on the likelihood, essentially. So from their seminal paper, a lot of work has been done. People have made these kind of studies for various types of models. So the standard ones, like regression, density, classification. You also have like high-dimensional models, large p, small n, recently, using spike and slab priors, covariance estimation, completion matrix, inverse problems, linear inverse problems, and sometimes nonlinear inverse problems. So now, more and more, you find results on more and more complex models. So it's not only the baby models that are studied anymore. You also find some more modern models which are non-exchangeable, typically, because like nonparametric HMMs and things like that. So they can be handled more or less with more or less difficulties using the theory that I've described just before. And also, various families of priors have been studied for all these models with different variations, of course. So there is a general theory for Gaussian processes or hierarchical Gaussian processes, mixture models, and so on and so forth. One of the sort of interesting things that you get out of it is the fact that one of the strengths of Bayesian modeling is the hierarchical Bayesian modeling. It's because you can add hierarchies. When you add hierarchies, you add flexibility, and by adding flexibilities, you are essentially getting more adaptation. So you can adapt to various things that you don't know. So for instance, if you're estimating a curve and you don't know the smoothness of the curve, you can learn from the data the smoothness of the curve by putting a hierarchical prior. Typically, you put a hyperparameter that drives the curves, and you put a prior on these hyperparameters. It can be a number of components in the series. It can be anything like that. So there are various ways of building hierarchical priors. Each of these ways will lead to some types of adaptation, which is interesting. And so all these models have a hierarchical version of them that gives you adaptive rates, but adaptive rates in a certain sense. So I'm going just to illustrate in a specific simple model just how we get things like that. So imagine that you have RID data with density f, which is unknown, and so you're modeling f as a mixture of Gaussians. It's a bit like a kernel estimator, but it's better than a kernel estimator, essentially. So this is the Gaussian, and I'm looking only at location mixture, so you're mixing only the location, and sigma, the variance of your mixture, is the same for every component. And you put a prior on P here. So you can make we consider discrete priors. So you can look at as a Dirichlet process that Mike was talking about, but it can be any kind of sort of generic discrete prior, where you can put a prior on K or not, and you can put a prior on the weights given K, and the mu G are typically RID with a base measure G. There is this hyperparameter sigma, which drives the smoothness of your curve, essentially. So you can put a prior on sigma by saying it's like typically an inverse gamma. If you do something like that, and so you're reasonable here, what happens is that you can prove that for every Hölder alpha ball, so for every alpha positive alpha, if f naught or log ff naught is locally Hölder, I'm not going to describe exactly what it means, but it's sort of understandable like that. Then you concentrate, the posterior distribution is going to concentrate for the L1 norm here around the truth at the rate which is up to a log-n term, the minimax rate, n to the power minus alpha over 2 alpha plus 1. You can make it multivariate and so on. It doesn't make a difference. And so here what's interesting is that in your prior, you don't know alpha. The alpha appears nowhere in your prior. And the posterior distribution is actually capturing the right alpha so that you get the correct adaptation rates for the true alpha.
F0 is alpha, it's Hölder alpha. Is it the same also if it's log f, which is Hölder alpha?
So the theory, you can prove that within this class of locally Hölder function, this is a minimax rate as well, up to a log-n term again. So there are log-ns here. There are log-ns in the Bayesian literature that are typically here for technical reasons, sometimes not only for technical reasons. So this is so you can see by using this hierarchical modeling, you get adaptation, and it's costless in the sense that for a Bayesian point of view, it's natural to put a prior on sigma. You don't even think about not putting a prior on sigma actually, and you get an adaptive estimator for free somehow. So there are a few issues there still. As you've seen here, I got it with the L1 norm. If I had considered instead the sup norm for f naught, if I wanted to have concentration on the sup norm, the story would have been completely different. And one of the reasons is the fact that in the theory of Gaussian, Gaussian, van der Waals, here you have this testing condition, and you need to be able to construct these tests that have a separation rate epsilon n with a second type error, which is exponentially small with the rate epsilon n as well. And that blows up each time you don't have a D which is naturally linked to the likelihood. Like the L1 is correct, the Hellinger would be the same. If you are in regression, you'll get L2. But if you are with a sup norm, then you don't get something like that as nice. And if you follow this procedure and you're working on the sup norm concentration rates, then you're going to have suboptimal rates. And you can prove actually that for any kind of D loss function that's not natural somehow, if you follow this procedure, you're going to have a suboptimal rate. There is a general theory that we have worked on where we have a lower bound. Where was I? I wasn't there. So that's one of the issues is that if you have a different type of loss function, you have to work harder. It's not impossible. You can get rates as well, but you can't follow the general theory that was developed by Gosal-Gosch and van der Waart, and it's a lot more work. And actually, the quantity of work that you have to do for that is actually related to this kind of quantity of work here. Another issue is that what do these posterior concentration rates tell us? What kind of information do we have? Is it only on point-wise estimators, or does it also give us some information on coverage or credible regions as well? So for sure, we get these concentration rates give us some insight on the frequency risks associated to D. For the credible region, it's not clear. The only thing that we can say is that if you have a credible region with like a credible ball associated to D, for instance, then on average, the frequentist coverage is going to be 1 minus alpha, but not at all uniformly in theta. It's only on average. So that's only a Fubini here trick that gives us this answer. And so the question is, can we sort of give the set of theta for which we have a good coverage and the set of theta for which we won't have a good coverage? And that's what I'm trying to explain now. There have been some work on that. It's a bit still the beginning, so there isn't much. One of the work, I think, is promising, and it's quite interesting. And it's a work by Castillo and Nicki, where they essentially what they do. I'm going to describe what BVM is, Bernstein-von Mises theorems are. But the idea is that they are looking at a very weak BVM. So it's not a BVM in a strong word, but it's a weak BVM. And by looking at this weak BVM, they are able to get some results. So they are able to construct some credible regions that are also confidence regions to some extent by changing them a bit. And but before that, when you look at confidence region, you are interested first of all of the fact that you have a good coverage, but also in this radius. And what happens is that if you have if you have a concentration rate, and you consider a credible region associated to the same D here, the usual credible region, then you know that the size of your confidence of your credible region is correct. So you have the minimax size. So the question is really, what is the coverage of C alpha? The size is correct, but the coverage you don't know. And that's where Castillo and Nicki have found a good tree, at least in some example. So their setup is the following. It's a very baby model. You have a white noise model. So you have a curve, and you expand your curve and your data on a wavelet basis, typically. So you have an infinite series of observation, X, with an infinite series of mean, and Gaussian noise with variance 1 over n. So this is like the typical baby model. And if things don't work in this model, they don't work anywhere else. And also, then it's also a model that's a sort of an example or a symbol of a lot of models that look like them, essentially. So what they do is that they put a prior on theta jk. Like they are independent with some, they are Gaussian, let's say a Gaussian prior, for instance. You don't have to be Gaussian, but they are a Gaussian prior. And then they derive some condition to get a weak BVM. I'm not going to describe exactly what that means. And using that, they are able to construct for the sup norm a confidence region, really. So it's a credible region to begin with, but it's not a credible region in a sup norm. It's a credible region in a weighted sup norm. In other words, the Wj goes to infinity. And so here you're weighting them down a bit to not be bothered by them somehow when the j gets too large. And when they prove is that if you construct these regions there, then you have the right this is a credible region, but you have a right confidence level. And the question is, what's the sign of that? Obviously, because you have weighted these downs, it's too big. And so you can take off a part that makes it too big, and then you have a right confidence and credible regions. It's a bit artificial in terms of construction, but it's efficient. The question is, can we make it more general than that? For the moment, there is nothing outside this kind of Hilbert structure. Like for more complex geometry, we are nowhere close to be able to say something like that. Yes.
So what are the W's here? I mean, they are our parameters. They're parameters of the problem that you put, or they're just numbers that come out of the analysis. I'm confused.
So that these W's, these WGs, they can be anything that goes to infinity more quickly than j, square root of j. They are not in the prior there, so it's not something that you put in the prior. It's something that you put in your construction for your confidence region. Okay. So, but the prior. So if you were to do only point estimation, you wouldn't look at these WJs. You would only look at the posterior distribution and take the posterior mean, and you'd get the result. But here, if you want to have measures of uncertainty, so you want to construct a credible region that has also good frequencies coverage, then you weight things down with these WJs, and that's what they do. And you chop off the theta that are too big, essentially, in the Hölder norms. And when you do something like that, then you have a credible region that's also a confidence region.
But I mean, this doesn't tell us anything about the size of the credible region? Or?
Yeah, actually, maybe I didn't put it, but actually you can prove that this has a right size. So it has the so if you pick up the WG correctly, and UN correctly, so more like that. If you pick up UN correctly, and it depends on your gammas, then it has a right size. And they have a way to make it adaptive, to some extent. But it's a long story, so I'm not going to describe everything. But the thing is that you can sort of mimic the frequencies literature by looking at a Bayesian object and sort of naturally modify it to get something that has good frequencies properties. The question is, how can you do that outside this white noise model or any model that's equivalent to the white noise model? For the moment, we don't know. There is another paper which is also interesting by Boton, Szabo, and Ad van der Waart, and so on, where they consider a credible ball for the L2, for which they blow up a bit the radius, and they have a confidence. They have a good confidence region for this one, but only on a subset of true parameters, so not uniformly, and that's called the Polish tails. I'm not going to describe more about that, but they're sort of what I want to say is that now people are more and more interested into these kind of ideas because statistics is not only point estimation, but it's really a measure of uncertainty. Bayesian is great for measures of uncertainty because you have the whole posterior distribution. And the question is, how can you interpret this measure of uncertainty if you don't know much about if you're not sure about your prior? And this is in these large complex models, in these large or infinite dimensional models, there are all sorts of parts of your prior that you don't really understand because it's such a complex object. And so it's important to have these guarantees that Mike was talking about. And looking at the frequencies coverage of these credible regions is one way of getting a guarantee of this for your procedure. But as I said, it's a much more complex question than just looking at point estimation. Point estimation, now we sort of know how to do it. Credible region, we are just starting, and there is a lot more work to do there. Now, what I was showing is getting credible regions for the whole parameter. That's asking a lot. If your parameter is infinite dimensional, you're asking a lot of things. You could be more tune down a bit your ambitions by saying, I only want to look at some aspects of my parameters, which is like some functional of the parameter, and I want to have good measures of uncertainties for these aspect of your parameters. And that's where semi-parametrics comes in. So you have your parameter is infinite dimensional, but you're only interested in a finite dimensional part of it, so a functional of it. So it can be such that a model for which you have a split, a natural split between a parametric parameter and a non-parametric parameter, if you see what I mean. like in the Cox model, for instance, or other models like that. But more generally, you can think about it as you have a parameter and you're looking at a function of it, like looking at the CDF at a given point or the mean or whatever. So you have all sorts of functional that can be of interest. And the question is, if I want to have something more precise than just concentration rate on these parameter, can I say something? Because I'm looking at something which is simpler to some extent. It's simpler, but yes and no. So what are the things that I want to look? I want to see if I can say whether what I observed in the parametric case is still the same, which is the posterior distribution at theta going to look like a Gaussian distribution? What would be the center of this Gaussian distribution if it did? And what would be the variance of this Gaussian distribution also? And that's what BVM is about. So that's just what I was saying. So Bell transform indices have been developed in the frequencies in the parametric world for a long time. It's something that's known for years, for decades even. And everybody says in regular parametric models, you also the posterior distribution is going to look like a normal centered at the MLE with the variance, which is the inverse of the Fisher information matrix. And so there is a duality between the frequentist distribution, asymptotic distribution, and the Bayesian asymptotic distribution. They are the same. And so if you look at the credible region, it's going to be also a confidence region because of this duality. What can we say about that in the that I've said before? So in the non-parametric framework. So how does it work? Before we can say something in the non-parametric framework, how does it work in the simple parametric framework? It's a very simple idea. There is nothing exceptional about it. So if you are in a regular model, so you have what we call a LAN expansion. Essentially, the log likelihood looks like a quadratic form locally. If you have a local log likelihood, which is log likelihood which is locally like a quadratic form, if you are concentrating on the truth, there is all sorts of variation on these. And if the prior density, the prior has a density with respect to Lebesgue measure, which is positive and continuous, it looks like a very stupid condition here in the parametric framework, but it turns out to be the worst condition actually in the non-parametric framework. Then the posterior distribution is going to be asymptotically normal with the mean, the MLE, and the variance, the inverse of the Fisher information matrix. There have been all sorts of extensions to non-regular models and things like that in the parametric framework. But what I want to talk about is what happens in the non-semi-parametric framework. So what happens? So typically, here I recall what we are. We have a non-parametric model. Theta is infinite dimensional. We are interested in psi of theta, which is finite dimensional. And we want to know whether it's asymptotically normal and what are the centering and the variance. So we have conditions that look like the conditions that existed in the parametric case. In other words, locally, the log likelihood must look like a quadratic form. Otherwise, there is no Gaussianity behind. And so if you look at theta close to theta naught, then you have like a quadratic form. This is the quadratic form here. This is the linear part. And this is the remaining term. It doesn't have to be really small uniformly, but it's just a remaining term. You need to concentrate. So you need to be close to your truth, but the epsilon n can be anything going to 0. It doesn't have to be very small. So you are locally Gaussian. You are locally quadratic. You concentrate around the truth, and we're looking at some functional that are smooth. In other words, if you can make a Taylor expansion of the functional, and you have a linear part and a quadratic part, and you can have other parts. And I'm only going to describe, for the sake of simplicity, what happens in this case when you have a linear approximation of your function. But you can extend it to the quadratic approximation as well. And so what can you do? So if you have these LAN condition, you can concentrate and you have a smooth functional. Then what you're requiring is that this ratio goes to 1. It looks like nothing, but that's actually the worst condition to check. So what is this ratio? Essentially, you're looking at the same integrals, but instead of looking at the likelihood at theta, you're looking at the likelihood at a shifted version of theta. So it's theta minus something which is small. But because theta is infinite dimensional, this might not be so close, actually. And so what you're asking is that this ratio goes to 1. And so if this ratio goes to 1 under the above framework, then you have BVM. If this ratio doesn't go to 1, then you don't have BVM. So it's a necessary condition. So as I said, the first, the LAN, the concentration condition, and the smoothness are very like natural conditions, and they are not very sophisticated, except if you have a very complex models. And so the difficulty really is for checking this that the ratio goes to 1. The ratio of these two. So it's any t, but it doesn't have to go uniformly over t. So you fix t, and when t is fixed, you have to go to 1. And what does it mean? If you were if theta was parametric, so finite dimensional, so theta t is close to theta with an order 1 over square root of 1 of n. If your prior is positive, has a positive and continuous density, then this becomes true. So the density at theta t is the same as the density at theta plus something which is small, and so you can neglect the rest, and so you don't have to worry about it, and the ratio is going to 1. But when you are infinite dimensional, you can think of a prior in this infinite dimensional model as typically, I call them Swiss cheese, du Gruyère Suisse, because it's full of holes. There are more holes than the rest of actually cheese. And priors, non-parametric priors are the same. It's like, essentially, it lives on very small, a bit like, compared to L2, for instance, if you put a Gaussian process, the Gaussian process doesn't live on the whole L2, but it lives on something very small, but the support, the close, la fermeture, the closure of the support is essentially L2. But you can think about it as living on something which is much smaller than L2. And that's where you run into trouble, because you cannot make this change of parameter anymore. Because theta has a sign in the prior, but theta t might be in a hole. So it doesn't mean anything. And so the question is, how can you do something like that in this infinite dimensional model to prove that you have this ratio that goes to 1? And so that's what I was saying. And I'm going to describe it in an example. So for the kind of functional that we looked at, but you could imagine others, like for instance, if you look at density and you look at the entropy, if F0 is smooth enough, then you can approximate the entropy by the linear part. Otherwise, you have a quadratic term that comes in. You can look at a linear functional, so the mean of something with respect to a functional. And we just, for the sake of illustration, I'm going to look at a prior that puts mass on piecewise constant functions. So random histograms, essentially, with the splits, so the bins that are regular, and it's only the weights and k that are the parameter in my prior. And I get adaptation through k, and the weights, I put like a Dirichlet prior on them, which is typical. So it's a very basic prior, and typically for estimation, you don't really use this kind of prior because it's so simplistic that it's not very good. But so my question is, what does it mean to make this change of parameter from theta to theta t with this prior? So remember that if k is fixed, theta lives in Rk, so it's a k-dimensional vector. 2 minutes, okay. But whereas theta t, it's a function, because it's a theta plus a function that doesn't live in Rk, it lives in R infinity to some extent. It has an infinite, if you want to, you can approximate it with a finite dimensional object, but it's an infinite dimensional object. And so the best that you can do is you project this term on the k-bins, and then you have a remaining term. And what's going to happen is that if this remaining term is small enough, then you are not in trouble. If this remaining term is not small enough, then you are in trouble. And it all depends on k. And k is in the posterior distribution. And so if the posterior distribution concentrates on k that are too small, you don't have BVM. If the posterior distribution on k don't concentrate on k that are large, then you are going to have BVM. And then you have a conflict, because if you want to estimate theta well, you might want to have a posterior that concentrates on small k's. And so in this case, to have BVM for a wide varieties of functionals, you want to be non-smooth somehow. You want to be bad for theta, but good for psi of theta. And you cannot be good for both somehow. If psi of theta is not so regular, then you're not going to be good if you have a good prior for theta. And that's sort of the general idea behind that. You can find other counterexamples. I don't have the time to sort of dwell on that. And I jump to the conclusions. So essentially, what I said is, so now more and more people are interested in looking not only at the whole parameter theta, but also more on some specific aspects of the parameter. And what happens is that, or the way I see it, is that you have a prior that lives in these infinite dimensional objects. So it's a complex prior. They are good for some things, but they are not good for everything. And so it's important to understand what they are good for and what they are not good for, essentially. And looking at the asymptotics is a way to trying to understand a little better what they are good for and what they are not good for. If you look at convergence rates, you have a partial answer. If you look at measures of uncertainty, you have another kind of answers. And now more and more people are interested in getting sort of away from the likelihood. What I mean by that is the fact that if you are in a you're interested in only a finite dimensional part of like the mean of your function, for instance, or something like that, or the expectation of some functional of under your model. If you construct a whole non-parametric model for that, it's possible that you will be really bad for your functional of interest, because essentially you are sort of drawn by the non-parametric part somehow. And so you have to, if you are really interested in something specific, you have to think hard about the way to construct your prior such that it doesn't kill the semi-parametric part, the finite dimensional part of object of interest. And the example of this linear functional for the histogram prior is typical. It's not like, because it's only a specific example, it's true for many, many families of priors. And so what people have come up is to try to construct different types of likelihoods. And maybe there is something, so we are sort of getting a bit away from the Bayesian framework somehow, away from modeling. If you have a loss function, somehow maybe and a semi-parametric loss function, maybe it's better not to look to construct a whole likelihood if you want to be robust. It's a maybe. One of the objections I have for these approaches is the fact that if you have many functional of interest, then you have to be coherent, and it's not very good. So then it might be better to construct a full likelihood somehow. But you have to think hard on how you do it, and it's not because you're good for some of the aspect of your parameter that you're going to be good for everything. Other things that are important is the fact that so far, all these results that are like precise description of the asymptotic behavior of the posterior distribution, like coverage or BVM, they have been only proved in simplistic models. So white noise or regression with simple priors. But each time you get out of these, like say, basis expansions, like because of even the histograms, you can look at it as a bit as a basis expansion. Each time you get out of these sort of basis expansion families, we have no idea on how to answer these questions. And so there is a lot of work to be done in this area. Like for mixture models, for instance, there is nothing, both for coverage and BVM, nothing has been done. And it's a very complicated, area. And so if you want to work on that, you're welcome. Thank you.
Do you have any questions? So actually, I have a question. At some point, you said that when you're moving along this direction of the gradient of psi, you might fall in the hole which is not in the support of your prior. I mean, is it reasonable to think that you might have a prior that has support on a smooth manifold, and so that you could actually move along the geodesic of your manifold rather than just trying to go in this random direction?
So the thing is that yeah, it's here. Yeah. The thing is that the direction is completely driven by the functional that you're looking at.
It gives you the tangent space, but then you could just move.
So what you really want to do that. The question is you cannot necessarily. So what you want to do is so there is a different aspect of your question. So this psi dot 0. This direction, as I said, it comes from where am I? It comes from the Taylor expansion of the functional. So this is this point, and so this Taylor expansion is dependent on the geometry associated to the LAN expansion. So what you're saying is that but LAN expansion are not unique. It depends on the kind of submodel that you're considering somehow. So you could imagine that if you know that you are in this manifold, then you could look only at this submodel along this manifold and then has something that's more associated to this manifold, and that's how you could get a better result. And I think like for the examples that we had before, we had counterexamples. In other words, we could prove that you don't have BVM. You have a bias that comes in because of these terms of the bad approximation of theta t by this submodel somehow. But for instance, if you look at mixture models, that's a direction to go. We don't really know how to do it yet, but it's sort of the direction to go.
Another question? All right, so let's thank Judith and all the